and very good morning to all of you. My dear students, ladies and gentlemen, I hope you had a good night and you had rested well. Let us once again discuss how we can identify that the functions are convex or concave. So in this video, I'm going to explain how a function could be convex or concave when y is a function of x when this is one variable case. In the coming one or two videos, I'll explain the case of two variables, and I'll use complex mathematics and some other functions to prove that what is concavity, what is convexity, and what is quasi-concavity and quasi-convexity. So this one is a little bit simple. So my dear students, I hope and I understand, I reckon this is a common sense that you have studied some differential calculus, and the study of differential calculus shows that how the sign of the first derivative determines whether a function is increasing or decreasing on an interval I. If the derivative of x is greater than or equal to 0, that is, if it is non-negative, then the function f is increasing on I. And if the derivative of f of x is less than or equal to 0, that is, if it is non-positive on interval I, then the function is decreasing, and vice versa. You might also have studied the second derivatives, and the second derivative f double prime x is the derivative of f prime x, that is, it is the derivative of the derivative. Hence, if the second derivative of x is greater than or equal to 0 on interval I, then it means that the slope of the function is increasing, that is, that function is increasing on interval I. If the second derivative of x, that is f double prime x, is less than or equal to 0 on interval I, then the first derivative or the slope of that function is decreasing on that interval. Let us focus on these two graphs. In the first figure, the slope of the tangent increases as x increases, so the first derivative of x is decreasing. And this is the equivalence of the equation 1 here, where the slope of the tangent, that is f prime x, is increasing as x increasing. On the other hand, the second graph shows the case when the second derivative of x is less than or equal to 0 on interval I, and f prime x is a decreasing function. So the slope of the tangent to the graph in this figure is decreasing as x increasing. So keep this in mind. Here, suppose that the function is continuous in the interval I and it is twice differentiable in the interior of the interval I, then we can introduce the following definitions. This graph shows that this is increasing convex, this graph is increasing concave, this one is decreasing convex, and this one is decreasing concave. So a function f is convex on interval if and only if the second derivative of x is greater than or equal to 0 for all x in the interval. Similarly, the function f is concave on interval I if and only if the second derivative of x is less than or equal to 0 for all x in the interval. Now let us check the convexity and concavity of the following functions. A, where the function y is equal to y is a function of f, y is a function of x, is equal to x square minus 2x plus 2, and another function is ax square plus bx plus c. Now first let us solve the first equation. So here the derivative of the f of x is equal to 2x minus 2, and the second derivative of this function is equal to 2. Since the second derivative is greater than 0 for all x, then f is convex. So this function is convex. Now take the case of the second function. Here the derivative of the f of x is equal to 2ax plus b. So double prime f double prime x, that is the second derivative of x, is equal to 2a. If a is equal to 0, then the function is linear. So in this case, if a is equal to 0, then the second derivative of the function is equal to 0, then this function is linear. In this case, the function f meets both the definitions in 3. That is, it is also convex as well as concave. So it is both concave and convex, such a function in which a is 0, and if it is linear, then it is both concave and convex. If a is greater than 0, if here a is greater than 0, then the second derivative of x is greater than 0, so in that case function will be convex. If a is less than 0, then in that case the second derivative is negative, and the function will be concave. We consider two typical examples of convex and concave functions. This is the case of the word population from 1500 up to 2000, and this is the word population. So this is a kind of increasing function, but the rate of increases. So each year the increase becomes larger. So this is increasing convex function. This is the wheat production. Let me explain this a little bit more. So for the last 5 centuries, population over time has been convex. This graph here, the second graph, shows the wheat crop, where y is a function of n, where n is the fertilizer per acre used, that is in pounds. So y depends on fertilizer, y is a dependent variable, n is an independent variable, n is the amount of fertilizer used per acre. This function has a maximum at n is equal to n naught, and that is approximately equal to 172. So here the wheat production is maximum. After that, if we increase the amount of fertilizer per acre, then the total product of wheat will decrease. So increasing the amount of fertilizer beyond n naught will cause wheat production to decline. Moreover, this function y function of n is concave. If n is less than n naught, then this function is increasing by 1 unit will increase. Increasing n by 1 unit will increase production of wheat by less than 1 unit. The larger is n. Similarly, on the other hand, if n is greater than n naught, then increasing n by 1 unit will decrease production of wheat by more than a unit. So the larger is n. Let us also examine the concavity and convexity of some other production function, where y is equal to a k raised to the power a, and this a is positive and a is also positive. These are two constants. Now this function is defined for all k, where k is non-negative, that is greater than or equal to 0. Let me first show you the... Okay, let us differentiate this function with respect to k. Then it means that y prime, or the derivative of y with respect to k, is equal to capital A times exponent of k and k raised to the power 1 minus a. And a second derivative of this function with respect to k yields that y double prime is equal to a into a times a minus 1 k raised to the power 1 minus 2. Now, if A is this interval in 0 and 1 interval, then the coefficient, then this coefficient is less than 0, so that the second differentiation of this function is less than 0 for all k is greater than 0, hence the function is concave. And the graph of function y is equal to ak alpha for 0 is less than a is less than 1 is shown in figure 6. So let me first show you figure 6 and 7. This is figure 6. So it says that the graph of y equals a k raised to the power alpha for 0 less than a is less than 1 is shown in this figure. Here this exponent of k, a is between 0 and 1, but it is greater than 0, but it is less than 1. So it is in between 0 and 1. On the other hand, if a is greater than 1, then the second derivative of this function is greater than 0 and y is a convex function of k, and this is shown in this figure. So finally, if a is equal to 1, then a is linear, so that function will be both convex and concave. So this is strictly convex, this is strictly concave, and if this was linear, then it would be both concave and convex. So ladies, this is a very simple and easily understandable video on the concepts of convex functions and concave functions. I hope this is quite informative for you. But remember, in the coming video, I'll explain the convex sets and convex functions, concave functions, and quasi concavity of the functions that is widely used in consumer theory and in the demand theory and the maximization of utility or minimization of expenditure in the microeconomic theory. So kindly subscribe to the channel and don't forget to click on bell icon so that you could get regular notifications about other videos that I'll upload for you soon. Thanks for watching. Kindly subscribe to this channel and share its various videos in various WhatsApp groups so that these could reach to the maximum